Good afternoon, everyone. My name's Darren Wolf. I chair the Building Simulation Group, and we, the Building Simulation Group, welcome you to the CIBSE Building Simulation Awards 2022. So we've got an action-packed hour and 10 minutes for you. I will start with this welcome, and then we'll be moving on to the main award for the Building Simulation Award and the presentations there, followed by the Young Modelers Award. Then I'll be giving a quick overview of the Building Simulation Group activities, followed by an overview of TM69, dynamic thermal modelling of basic blinds. Then we've got the presentation of the awards by the judging panel. Before we get on to the awards, many of you may know that we are celebrating 125 years, CIBSE, and our president, Kevin Mitchell, has challenged us to celebrate, inspire, boost, share and engage. So I'd encourage you to go onto the CIBSE website /125 and see how you can participate in those activities. So this is the Building Simulation Awards. We're celebrating the best of building simulation, and we're hoping to inspire the next generation. So I'm going to now pass you on to Vasiliki, who is head of our judges, and may the awards commence.
Can you? Yeah. Okay. Great. Hi everyone. I'm Vasiliki Curioso. This year, the honor of being the head judge. You can tell it's the first time I'm doing this. I've been in the industry for 8 years in building simulation. I'm currently doing smart energy integration doctoral research at UCL and Borough Huckle. I've been in the group for a few years now as a committee member and as a group secretary lately, and a judge since 2019 for the awards. So heading over to former judge.
Yes, I used to be head judge. I'm Darren Coppins. I'm director of Built Physics, and I've been in this industry now for over 30 years. No, I don't look old enough, thank you very much. Yeah, really looking forward to it, as we do every year. The last 2 years we've been online doing this, and this year we're back in person, which is great, so really looking forward to some great presentations.
Thank you. Welcome everyone. This is Baran Tanrıverdi. This is my first role as a judge as well. I'm a mechanical engineer in the background, working for Mod McDonald's as a principal building physics engineer, and I can say that I spent my last 13 years doing hands-on modeling and enjoy the art.
Thank you. Pleasure to be on the panel with you. A little bit of how we're going to run the order of the awards today. We're going to start with a presentation of the shortlisted presenters for the main award. Thank you. You can see the 6 shortlisted presenters. One of them is joining us online from Spain. The rest 5 presenters are here, so we're going to quickly get on to the presentations, followed by short QA sessions for each of them, and then the judges will go off and deliberate. And while we do that, Gabriela Costa, our committee member, is going to introduce the Young Modeler shortlist and say a few words about them. We're then going to come back and announce the awards. Thank you.
Yes, I think I'd just like to add that we haven't pre-decided any of these 6, so it's all in the 5 minutes that each of you have. No pressure.
Thank you, Darren. Yes. Good luck. We're going to start with Haytham Al-Rasbi. Thank you.
Hi everyone, my name is Haytham Al-Rasbi. I am a PhD student at University of Nottingham, building physicist in Rolton Group. And today I'm presenting my part of my PhD research, which is building simulation of traditional and contemporary mosques in the Sultanate of Oman. So the objective of this research or this simulation is to improve the current building's thermal performance using methods learned from the vernacular architecture in Oman. Where is Oman? Oman is an Arab country located in the east of the Arab Peninsula, near United Arab Emirates, Saudi Arabia, and Yemen. And Oman is very hot temperatures. It reaches high air temperature, mean high air temperature of almost 40 during the summer, and it can reach a daily temperature of 50 degrees. So the research methodology used here is computer simulation using TAS ADSL software. The problem with computer simulation is it's just a simulation and as accurate as the inputs that we put in. So the inputs that are used are literature review, field measurement, observations, meteorological data, and electricity bills. Those inputs are also used for validation, for data triangulation, to make sure that all the data are validated. And then the outputs of the simulations are used for suggested improvements, for data analysis, for discussion, and for results and recommendations. So the case studies that I have here in my research computer simulation are 4 mosques. 2, the first mosques are contemporary mosques built in 2015 and 1994. The second, third, and fourth mosques are traditional mosques. They're about 500 years old. Here are external pictures of the mosques. You can see Mosque 1 is built with concrete, clad with marble. Second mosque is built with concrete as well, painted. Third and fourth mosques are built with clay and clay walls, clay roofs. And here are internal pictures of the mosque from inside. You can see Mosque 3 and Mosque 4. They're built with clay, so you have arches, you have the thick walls, thick columns. The thickness of the walls can reach up to 1.5 meters. One thing to notice, since I'm taking into consideration the mosque and some of them are historic and traditional buildings, actually those kind of buildings are exempt here in the UK from building performance, which is interesting because some of them have some character and you don't want to modify those buildings. But I think it's interesting to study them and study because there's so much innovation in terms of design and also in terms of thermal performance. So the results of the computer simulation, the highest thermal loads as per the results are solar gain, external conduction gain, and sensible gain. And in order to improve those, we can improve the windows, improve the walls and roof, improve the thermostat set point. So what we did here, I did 9 different simulations. For each simulation, I changed one element or one thing of the simulation. So for the first one is changing the U values to reduce by 50%. Second, B2 is to change the concrete from the walls from concrete to clay, and the same for the roof, same for the windows. And the B8 and B9 simulations is to add 1 degree or 2 degrees Celsius to the thermostat set point. Now I'm going to show you the results. So the results are, I think, very good for most of the simulations. We have very good results for very good cooling reductions. And also I combined all of the simulations in one simulation, which is B10, combined one simulation of each building element, and it came out to be 38.8% reduction of cooling load for Mosque 1, and 27 for Mosque 2, 18% for Mosque 3, and 23 for Mosque 4. So as a conclusion, cooling load reductions of 38.8% could be achieved using vernacular architecture methods. Thank you.
Thank you very much for your presentation. I've got one quick question for you. On your slide of your results, it showed that for the clay constructed mosques, the night ventilation had a negative impact.
Yes.
Why do you think that was so different from concrete?
Because So you can see Mosque 1, Mosque 2 are built with concrete. They actually has a good reduction for Mosque 1 and 2, but Mosque 3 and 4 it actually has a negative impact. It increased by 50%. I think due to the thick walls, the thermal capacity, and also the time constant of the walls. That's why it had an adverse effect.
Okay. What sort of nighttime temperatures do you get there?
Nighttime temperatures. It depends on the summer or during the winter. Well, I would say about 10 degrees less.
Okay. Thank you very much.
Okay. Thank you very much.
Thanks.
Thanks everybody. I'm Jonathan Reynolds and I'm happy to present this work on behalf of my Arab colleagues, a study for the Climate Change Committee which looked at addressing overheating risk in existing UK homes. So I'm sure this summer's heat wave all kind of brought home how the buildings in the UK aren't particularly well adapted to very warm temperatures, and unfortunately this is something that's likely to get worse as we have increased climate change. So the project aimed to address this was to first assess the current risk of the existing UK housing stock and map how that changes as we add in climate change. And then task 2 was to understand the effectiveness and the cost of different passive mitigation measures. And then task 3 implemented those passive mitigation measures and understood and extrapolated the results back out to the building stock level context. So most people should be aware of Part O, which was introduced recently to improve the resilience of new builds. But what about the existing 24 million homes that we've already got built facing the same challenges? And all this slide is trying to get across is, look how diverse the range of buildings is. It's geographically diverse, it's physically distinct, and it's been built using many different construction methodologies over a long period of time. It's unlikely to be a one-size-fits-all solution here. So we've got a pretty formidable challenge for this project of how do we produce detailed TM59 assessments of a representative enough sample in a reasonable amount of time. A traditional approach to something like this would be to model a handful of buildings, maybe 10 to 20, produce your thermal simulation model, understand your baseline overheating results, and then apply some mitigations and see the effect. But due to the small sample you have here, it's really hard to extrapolate that results out to the entire housing stock. So we took a different approach. We instead started with a stock model from our project partners' parity projects, and this informed our parametric variables so that we could later easily extrapolate that back out. We used the Design Builder software to model several different building archetypes, and then we extended that software with several EMS and Python scripts to let us do things like control window behavior, to automatically output TM59 results, and to measure other overheating metrics like the mean nighttime temperature, which can have a bearing on comfort. We put all this back into Design Builder's optimization toolbox, and we use that to automatically produce 2,400 simulations in the time that it would have taken to produce a handful. So hopefully you can see the kind of breadth and the richness of this data set can really give our project team some robust conclusions and let us really understand what's driving the overheating risk in the housing stock. We then apply our mitigation packages. We have 5 in total, and these increase in cost and complexity. We find the right mitigation package for each of our representative buildings in each of our climate scenarios, and then choose the appropriate one. Because we've started with a building stock model, we can then more easily extrapolate that back out to the stock and understand at a national scale, if we are to overcome overheating, what does that look like in terms of carbon emissions, capital cost, and energy consumption. So I'd love to give you more results, but unfortunately due to the length of this presentation, I'll just give you this snapshot. So this is the results of the simulations with no mitigations applied. The leftmost circle is the current weather file, and then we add in 2 degrees of global warming and 4 degrees of global warming. So a couple of quick takeaways. You can see in the south of England and London, we already have a overheating problem with many failing TM59 criteria B. As we move through to 2 degrees global warming, the picture gets much worse, with only homes in Scotland consistently able to pass that criteria. And then when we move towards the 4-degree world, that's a pretty doomsday scenario. And actually, to be comfortable, these homes probably need active cooling in about 90% of instances we've found. So my colleague is doing a bigger burst on this project tomorrow, so if you're interested in more results, then please do go along. Thank you very much.
You mentioned that it would be computationally quicker and comparable to 2,400 simulations compared to a handful of simulations. But in terms of skills, in terms of the modeler themselves, how intensive you think the process was, and also how replicable in smaller scales? Like, it's great to see the national scale, but if you were, the second question, I guess, the application would be at a more localized level.
So in terms of absolute time frames, to do the 2,400 simulations took longer in absolute time. But in terms of modelling effort for the time that we care about, the time that costs companies money, it was the same as producing a handful of models, and then because you have these parametric inputs, you just let it go, and it will change all these options for you automatically.
Very quick question from me. Did you do the Python scripting?
Yes.
You did. And did you know how to do that before you picked up this project?
I knew how to do Python scripting in general, but actually a little bit to learn to interface with Design Builder.
And do you think it's something that generally modelers can get to grips with?
Yes, there's lots of examples there already on Design Builder, a little bit of coding background, and I think you could adapt them to your purpose.
Excellent, thank you.
Thank you.
So, my name is James Crowley. I'm Senior Technical Consultant at Hilsa Moran, and I'm going to talk about a parametric approach to modelling TM59, in actually a very similar way to the last speaker. So, this is the project that we had. It was a bit of collaborative R&D with Hilsa Moran, Inkling, and the Department for Levelling Up Housing and Communities. We wanted, for the consultation for the Part O, we wanted to validate the simplified method by running a bunch of TN59 simulations. So we wanted to test 14 different glazing sizes and 4 possible aperture sizes, which is 56 simulations per model. And we also had 2 models, a test flats and a house, in 3 locations, which resulted in 336 simulations, which is quite a lot of simulations to do manually. I mean, you could absolutely do it, but since we use TAS, it's pretty bad. You would lose the will to live after a few of them. So the solution we came up with was to build a program to do it for us, which we've named the Parametric Tool for Internal Overheating, PATIO for short. So how do we do that? Well, first of all, we need an API. What is an API? It's basically just something that allows one piece of software to talk to another piece of software. So all we did was, we can get Visual Studio and Excel and TAS to all talk to each other, and we can just automate TAS, basically. TAS has a very good API. So what we want the program to do was, you pre-build your existing TAS model as normal, and we want the program to automatically change the window X number of times, then change the aperture opening factor Y number of times, then simulate X by Y models, then assess each one for TM59, and then produce a bunch of results for us to analyze. So here's a little demo of it in action. How do I play this video? The arrow button. So if you see on the left is the UI that I made, and on the right you can see all the TAS files being created. On the UI you have your parametric inputs like number of window sizes and apertures. So it's exporting the 3D models. And I've sped this up, by the way, because it takes about half an hour. And then it simulates them. And then reads the results, thinks about TM59, and then gives you a nice Excel file with all your TM59 results for the various rooms. You end up with something like this. This is for a bedroom. You can see that because of the nighttime criteria, it likes bigger windows with more openings. Makes sense. And then for a living room, it doesn't quite like bigger windows because you get so much solar gain in the day. And the results of what we did influenced the Part O document. So you can see on the left is roughly what we came to the conclusion of in our projects, and on the right is from the Part O document, simplified method. There are ways you can develop this further, so you don't necessarily have to stop at just automating glazing areas and aperture factors. You can also rotate the building around, change the weather file, change the constructions, change internal gains, add external shades. And also I experimented with doing a sort of 3D visualization thing on the right, where you kind of select your room and you can visualize the pass and failing. So if you want to learn how to automate tasks yourself, I highly recommend going on edsl.net/blog, and this guy, I think it's Andrew from EDSL, will teach you how. It's actually very useful. Thank you.
Thank you, James. You didn't mention the language that you did the programming in, did you?
It's C#.
C#, okay, thank you. Did you use this tool in any of live projects in building design?
We have used it in some projects, yes, to sort of inform design at an early stage, where you just produce a bunch of results and see what kind of works and what doesn't, what needs more mitigation, etc. So yeah.
Thank you. And I guess the wrapping up is because it's a lot of technical terms in that, the free vent areas and the glazing openable areas. How easy is to communicate that with design teams?
It's actually quite complicated. I mean, my director did a presentation on free vent areas for this group the other day, and it's like quite a lot of technical terminology. So I refer to that presentation.
Great. Yeah, thanks for a very clear presentation.
Thank you.
Sorry. How do you see the interoperability of the tool with others? Sorry? Interoperability of the tool.
My colleagues have used this tool, and generally they get on fine with it. Thank you.
So for the next one, we actually have David Sanchez Garcia presenting from Spain. The issue is he couldn't, of course, travel here today. So what he's doing, we have a pre-recorded video from him, and then we have him here on Teams for the Q&A. So hopefully everything will work. Fingers crossed.
ACIM stands for Adaptive Comfort Control Implemented Model, and it is an open source Python library that provides useful functions related to the building area simulations with set point temperatures based on adaptive thermal comfort. It is composed of three modules: data, run, and sim. Data is used for pre and post processing of data, run is used to automate the simulation runs, and sim is used to transform PMV-based or fixed set point temperatures, which you can see at left-hand side, to adaptive set point temperatures at right-hand side. Adaptive set points in ACIM have been recently studied in more than 10 research papers indexed in first quartile JCR journals and identified as an important energy saving strategy. However, this presentation will be focused only to the building simulation aspect of the project, which is the simulation module. So, how does ACIM transform the set points? Let's start from the user experience, and then we will dive into the internal details. Considering we have previously installed Energy Plus, Python 3.9 and ACIM, say we have a folder with some IDFs in it. So we just need to open CMD and run Python pointing at that path, and type 2 lines of code. From axim.c, import axis, hit enter, and then axis.addAxis, open and close brackets, which will call that function. After that, ACIM will ask the user to enter some information needed to transform the IDFs. Therefore, a coding or programming background is not needed to use AXIN, specifically to transform the set point temperatures. Next, as the name suggests, an EMS script named AXIS, which stands for Adaptive Comfort Control Implementation Script, is added. So let's see how works the most simplistic version of AXIS. Adaptive set point temperatures take the values of the adaptive comfort limits, whose calculation is based on the running mean outdoor temperature. Therefore, an EMS sensor named RMOD is needed. Also, we need to override the values of the scheduled compact objects used for the set point schedules, which is done by two actuators named ACST_value and AHST_value. Then, an EMS program and a program calling manager objects are added, which controls the calculation of the values and setting of the actuators depending on the RMOD sensor with two if blocks for the heating and cooling set point temperatures. This provides the first of the two main features of AXIN. IDFs with adaptive set point temperatures can be simulated with any EPW file, since adaptive set point values are calculated on the go based on the running mean outdoor temperature sensor. So that was the most simplistic version of AXIS. However, the actual version has 11 input variables the user can edit. For example, comp stand is used to choose among 20 comfort standards or models, and cat is used to select the acceptability levels 1, 2, or 3 for the European standard and 80 or 90% for the ASRAE 55. This leads to the second of the two main features of AXIN. It takes one or multiple input IDFs and generates one or multiple output IDFs, which can be highly customized based on the 11 arguments. So based on these two main features, multiple output IDFs combined with multiple EPW files can generate a large database of simulations considering adaptive comfort, which opens new possibilities to expand the scope of studies from local or national to continental or even global, and to carry out parametric studies. An example of this is a parametric study currently under review in which we generated a total amount of roughly 4,500,000 IDFs, which combined with other parameters related to the energy poverty, the number of instances increased up to more than 36 million. Adaptive set points have been identified as an important energy saving strategy. To provide an idea of the energy saving potential, a study carried out for London's climate shows a 27% energy savings for cooling, 37% for heating, and an overall 27% for total energy demand. This is achieved only by applying adaptive set point temperatures without any other improvement on the HVAC system or retrofit on the building envelope. I hope you enjoyed the presentation. My name is Daniel Sanchez Garcia, and if you have any questions, you can contact me via email. Thank you.
Hi Daniel. So we have Daniel here on a tablet, and hopefully you'll be able to hear his response. So Daniel, thank you for that presentation. Very interesting sort of analysis of how we could use adaptive internal conditions to reduce energy consumption. Have you looked at all at how that might actually change with our changing climate in terms of the increasing temperatures and the future weather files that we have, and how that might change internal conditions?
Yes, this is something I have. Actually studied a lot because, well, you know, actually the energy saving potential changes depending on the weather file. I mean, on the weather itself. For example, in case of what I showed in the presentation, in case of London, there is roughly a 27% energy demand, but energy savings. But for example, in Seville, it is 83%. So this is a huge impact also in climate change, because, well, as we may expect, the cooling demand increases, but it is not compensated with the heating demand, the heating demand reduction. So in the end, there is it is not compensated, and the energy demand increases as the scenarios advance, in the RCPs scenarios, for example.
Okay. Okay, no, that's very helpful. I guess then, as a follow-up to that sort of question, is this is sort of would apply in two situations: the initial modelling of the building, but also the operation of the building. So, are you looking at methods as to how this can adapt and operate with building management systems, or consider that at all?
Well, there is a few research articles in investigating that, because there is, for example, some of the University of Seville are applying actual adaptive set point temperatures to the building management system, and they are achieving significant energy savings. So I can't recall right now the values, I mean, of the energy savings, but this is something that it is currently under development.
Okay, no, that's perfect. Thank you very much.
Thank you.
Thank you very much. So, there we go. Yes. So the next one is Farah Husseini from Excel.
Hello everyone. Can you hear me okay? Okay, is it better now? Hello everyone, my name is Farah Husseini and I am a Senior Sustainability Consultant at XCO2. Today I'll be presenting the work we've done to develop a parametric tool for early design stages to assess overheating risks and daylight performance. As we all know, overheating is an issue of increased importance, and designing to mitigate the effects of overheating can have unintended impacts on daylight. Therefore, this tool or this project aimed to develop and validate an early stage parametric tool to assess overheating and daylight, and a further layer of optimization was added by linking costs from cost consultants to different design options. Now, why this is important? This is important because first, it allows the clients and design teams to assess the effects that they could have in the early stages, and second, because it allows them to understand the costs associated with the optimization of overheating and daylight at land acquisition stage. And in the wider context, making informed design decisions in the early stages give the team the best output with the lowest cost and effort, because we're still in the early stages. The tool was developed for a one-bedroom flat that is naturally ventilated in London, and the weather file used is London Weather Central DSY1. This is the final outcome. This is the user interface that the user will be using, and I'll explain how we achieved that. In terms of workflow, we first started by developing a schematic that fed into all the different stages of the script development. The software we used were Rhino, Grasshopper, Ladybug, and Honeybee, as well as Python, together with Colibri to run all the possible iterations. And at the end, we used Excel with VBA to develop the tool with a simplified user interface. Why these tools? Why these tools? Because the conventional dynamic thermal modeling is carried out on a case-by-case basis, which is time-consuming. And in the early stages, evaluation speed is the key concern. Parametric modeling, on the other hand, offers a more interactive, more interlinked approach between the inputs and the outputs, and therefore offers a fast and flexible approach. In terms of parameters, these are all the different parameters or the design variables that we looked into in collaboration with the architects. Things like flat floor, whether this is round, mid or top, the orientation, 6 different orientations, the windows widths and how far these windows can open, the G values, and as well as some shading options. And this resulted in circa 13,000 different combinations, meaning 13,000 different iterations. For the script development, the steps were first to build the geometry, then prepare the geometry for energy simulation, and then assign the materials, and build the profiles for TM59 internal gains and natural ventilation, and then define the parametric elements across all the different steps, and set and run the simulations, both the average daylight factor simulation and the energy simulation, to get the overheating results. post-process the results and build the calculator to get TN59 criteria, and finally link all the inputs and outputs to Colibri to run all possible combinations. We validated the results against IES by running various iterations to make sure we minimize the discrepancies as far as feasible, and at the end we also adjusted the thresholds for risk measurements to resolve any further offsets. And this is the front-end tool that I showed in the beginning that the user will be using. To the left-hand side, we have all the inputs which the user can choose from. And once these are chosen, the outputs are automatically updated. And we have the overheating risk, the average daylight factor, and the cost variance. And the tool also outputs a 3D of the daylight map. In conclusion, the tool offers a dynamic workflow to explore a wide range of options to optimize overheating, daylight, and cost, and it has been used by design teams to inform early design stages, early design decisions, and this is particularly important because the most fundamental decisions are often made in the early stages with little to no support of simulation engines. In terms of future work, we're looking into some updates to consider Part O, BRE, the new BRE guidance in terms of climate-based daylight modeling, more flat types, and the future weather scenarios. And these are some of the projects where the tool has been utilized. Thank you.
Thank you so much. I would like to ask what optimization method you followed to get the results, and also is it a shoebox modeling or all the rooms modeled individually and the interaction in between considered as a part of it?
Right, so to answer the first part of your question, the optimization method was by running Colibri. Colibri is a plugin to Grasshopper where I can't get back to that slide for some reason, but it's an iteration runner that runs all the possible combinations. So this acted as a database. We have all the 13,000 different results from all the different combinations, and then it's up to the client or the developer or the cost consultant or the architects on what they would like to optimize. Like for example, if they want to make more savings on the cost, if they want to still have acceptable range of overheating and daylight. So the optimization is really up to the user. It's like we have all the database and this is the user interface, this is all what the user would be seeing, and then they can choose their variables and make the judgment. And to answer the second part of your question, sorry, can you repeat that again?
Is the interaction in between rooms are considered as a part of it, or is it modeled as a shoebox?
Yes, so for this particular developer, the most common flat type is one bedroom flat. So we modeled the one bedroom flat as it is, and it has all the adjacencies in the model and everything, like as if it's within a whole building. Thank you very much.
Then last but not least, we're Tari Mahendra from Hiroshima. There you go.
Good afternoon. Can you hear me? Good afternoon. This is 10th Session Road, where we did advanced HVAC modeling work. So as a brief background, it was end of stage 3 when we were told to do this modeling work. It's a B&B project, so the contractor was already on board, and it was the first design for performance project for almost everyone involved in the project, so it was a very steep learning curve for everyone involved. But I think the key strength was that we had a very good collaboration throughout the process. As an initial point, we took the partial model and built into it all the details that were available. We spoke to the architect almost every day that we were building this. So you can see different fabric on the ground floor, middle floor, and upper floor. There is also columns where there is concrete instead of cavity walls, so that was incorporated as well. We spoke about the final color of the fabric so that the reflectance of the fabric is taken in account. We built the plenum zones, so because the lighting is installed in the ceiling, so the heat transfer is accounted for. And you will see in the next slides as well that the air goes through the plenum and the extract, so it was important to build these. We researched every element of the project. So, for example, the bin lift, how Cambridge does the bin collection, and to calculate the energy consumption. There are 2 different types of external lighting with different operating times, tray seating tape, car park fans. So every element is researched, and also we thought about how each space will be used. So, for example, will the security be going through the building once a day on weekends, and what's the impact on the lighting consumption for that? So we tried to build it as realistic as possible. As the office floor planes, they are divided into 2 tenancies, north and south, and each has a air handling unit. So the air handling unit itself is modeled in a lot of detail with everything. So the volume of the air is as per specification, the efficiency, so everything is built into this is task system. And this slide also highlights an improvement from the first issue of the report to the next. So on the first issue, we made a case for demand control ventilation. We did 8 scenarios comparing the initial specification to how it will change the energy intensity of the building if we incorporate the demand control ventilation. So this is that was taken forward, and this is an improved model where CO2 sensors are installed throughout the office zones. And you will see that the south air handling unit also supplies the toilets and showers, but the extract doesn't go through heat exchanger, so we had to model it separately. So the heating and cooling is done by VRF, and this information that you see below is the information incorporated in one unit. There is similar information for each unit specified in the project. We couldn't find similar information on this amount of information for the unit specified for circulation space. So we found an alternative that was matching, but that was a heat recovery unit. So what we did is we checked the demand for heating and cooling for the whole year, hourly, to see when the demand is happening simultaneously. And we only found 9 instances where that was happening, so we thought it was a good alternative to use. Domestic hot water is again VRF, and we incorporated the details that the manufacturer provided. This is again highlighting an improvement from the first model. So the specification was 65 initially, and through modeling work we were able to convince the design team to reduce it to 60. So with all these different scenarios, we were in the end able to reduce the energy intensity of the building by 8 kilowatt-hour meter square, and there is a high chance of the project now achieving 5-star rating. We also think that we have built this model in such a detail that we think if at post-construction the building doesn't achieve the energy intensity that we are thinking or envisaging, we will be able to pinpoint where the problem is and recommend rectification quicker than other projects. Thank you.
Thank you, Vaishalik. I have a quick question from me. It seems like a lot of complex input coming in and out of the project. I guess, where would you put the most pressure in terms of gathering the information of the actual modeling, which was also complex? What was the biggest challenge?
The challenge, which one do I say? I think the bigger challenge was understanding what I'm asking. So I think this was also the first detailed HVAC modeling for myself as well. So I had to very quickly understand what I needed to ask, and then ask the contractors to get this information for us, and also convince them to get this information because they were, as they said, they were also reluctant to contact the manufacturer in that way because obviously it reduces the opportunity to negotiation of the unit. So it was very challenging to ask the information and get the information. Yes. Great answer.
One very quick question from me. So with the neighbours modelling that you did, was you able to align your output with the metering that's going in the building?
The metering that...
So in terms of the data that came out of your model, in terms of kilowatt hours per annum, was you able to align that with the meters that are actually going in to allow that to happen once the building is in use?
Yeah, I think it's highlighted in one of the recommendations that we in the first issue of the report, we listed the improvement to the metering strategy that they have to do, and that was one of the recommendations that they took forward. So the initial three were the ones that they are going forward with.
Okay, very good, thank you.
So, Gabriela, it's your time.
Hi everyone, I'm Gabriela Costa. I'm a Principal Sustainability Consultant at User Simple Trust. And I'm going to introduce you to the Young Modeler Awards category and go through the 6 finalists today that some of you might be here. So we launched the award in 2020, so this is the first time I'm actually presenting to you in person. And it's been great to see how the industry has picked up on this award and how many entries we've got at the stage. So we had people applying from all over the world, UK, USA, India, Spain. So it's great to see that outreach of this category. So this year we have 6 shortlisted candidates shown here. And they range from graduate consultants to students, PhDs, and the submissions that they've provided, they cover energy, thermal modeling, ventilation, lighting, and microclimate for urban comfort. So it's quite a variety there. So starting from the right, I will go through what each of the candidates submitted so that you know a bit more about them. And first I wanted to say for all the shortlisted a massive congratulations because it's a very good place to be here. So shout about this and keep up with the good work. So Anmo, he is an architect with a degree in building energy performance. He is a co-founder of Co-LED. Is a performance-oriented sustainability and architectural office. And he's been working with clients and product research groups measuring impacts of their projects into savings in cooling energy. And he's been doing that through facade studies, outdoor thermal comfort, HVAC downsizing, modeling, and low energy systems design. He is very keen on expanding his knowledge from buildings to the city scale level. Priyanka Devi, she is a graduate at WSP in the Middle East, and she has won this year's CIBSE UAE Inter-University Design Competition. And the proposal that they had involved re-engineering a traditional wind catcher to provide outdoor thermal comfort using IES and ANSYS. So she's keen on facilitating low energy design, share information and collaborate. She set up, she mentioned an idea she had about setting up new groups for collaboration through like a common platform like Slack. Rima from User Projects, she's a graduate that is supporting local authorities in delivering low carbon and sustainable homes. Her entry featured a retrofit housing project with Central Bedfordshire Council, where 27% of CO2 emissions came from residential buildings housing stock. She investigated 3 phases of incremental improvements to retrofit, and the first being a soft touch retrofit, the second a deeper one, and lastly an all-electric solution retrofitting those homes with air source heat pumps. And she used SAP and PHPP to undertake the modeling. And her findings showed that for the phase 3 strategy, the council could achieve up to 90% savings in carbon and 80% in energy. Shweta, she's from Cardiff University, a researcher aiming to bridge the gap between the lack of carbon data available in India and policies in carbon emissions for buildings for the future. She demonstrated dynamic modeling capabilities on her submission, and her specialism is on multi-objective optimizations, similar to previous presentations. Her entry comprised of a study for an affordable sustainable housing scheme in Chennai region, and she optimized the building using passive and active strategies. And basically, she was testing comfort versus energy demand. She used a combination of tools and undertook simulation with Design Builder and One-Click LCA to also investigate the embodied carbon impacts. And then Vinit from Cyclone Energy has a master's in energy engineering, and Cyclone Energy Group is based in Chicago in the US. And Vinit is actively engaged with ASHRAE, CIBSE, US Green Building Council, and has shown us a variety of models that he's modeled over the years, so over 100 models that included high-rise buildings, historic renovations, industrial logistics, cold storage, and higher education buildings. And Cyclone Energy Group was awarded the 2022 CIBSE USA Outstanding Practice Award. Vinit aims to get his individual recognition today, and he hopes to give back to the community by developing knowledge forum platforms as well, so they can share more with college students and young professionals pursuing a career in the field. And last but not least, Vinuki from Alpin Limited, Heriot-Watt University. She is the group winner of the CIBSE Inter-University Design Competition 2022 that focused on the proposal for a smart wind catcher based on a combination of passive and active strategies. And she contributed to that award herself by analyzing the internal conditions of the surrounding microclimate and carried out the analysis using IESVE. She mentioned that she self-learned microflow and macroflow simulations and Apache HVAC. She enjoys seeing the results of the building simulation come to life with her digital twins. So this is just an introductory presentation to you. We're going to get the actual winner presented a bit later from the judges. I'll pass on to Darren now.
Thank you very much, Gabby. So I'll just give a very quick overview of the Building Simulation Group activities over the last year. So we were established in 2009. We try and do 2 or more seminars a year, and we've actually done 4 this year. We disseminate best practice, past presentations on the website, support publications and guidance to industry. So please do look at our social media channels. We've got a blog spot, and that's just a very quick overview. We've got really good outreach to over 12,000 subscribers, over 3,000 CIBSE members. Quick overview of the events. In February we had our part 2 of the Estimating Airborne Infection Through Simulation Analysis event. Speakers were Yu-Gi-Oh, Malcolm, Fred and Caroline. Then we had the Part L Volume 2 in September with Boan and Monica, followed by our Part O event with Susie, Jack and Ben. For that event we had 150 people joining, over 100 online and 50 in person. So we are sort of gathering speed and volume in these events, and it's fantastic, this combination of hybrid events which can improve our outreach. And then in October we had the non-domestic heat pumps event This was with CIBSE HVAC Group and IBIPSA England. We're trying to do more joint events as we can with Chalcon, Phil and Richard presenting. So you can pick up these events either on the CIBSE Build and Simulation Group website or the IBIPSA when we do joint events with IBIPSA England as well, and I'd encourage you to go there. We have a various subgroups, the CERT or certification group chaired by Ben. They do CFD, dynathermal and HVAC modules, and we're targeting completion early next year. The CIBSE Digital Department already engaged and ready to transfer the content onto the platform, and the lighting module has started, but we need volunteers for other modules, so please do get in contact with Ben if you can, if you're interested in the other modules, based on the AM11 chapters. Then there's the SBEM work with David leading that, and there was a call for evidence which is now closed. BRE and Sostanic going through the feedback. CIBSE participated in the workshop discussing the underlying methodology assumptions, and they're due to a scheduled catch-up in the new year with BRE and Sostanic to discuss the next steps. So that's a subgroup activity. Finally, publications. AM11 there's a possible update in 2023. The Hazim's email address is missing from this version, but if you can contact Hazim if you're interested in supporting this. We're thinking of extending various chapters, maybe bring in airborne reflection, air quality, extending the wind type studies as well, which I'll be involved with, and you can contact me on that. I'd now like to introduce you to Bahari, who's going to be talking about TM69.
Hello everyone. My name is Bahara Salehi. And it's a pleasure to me to give you an overview on the recent publication TM69 along with my co-authors Professor Darren and Gabriela, who are with us today, and Elpida, who is not with us. We all know about the performance gap between the simulation and the reality. And this performance gap and uncertainty in the modeling will be even worse and higher when it comes to the modeling of the blind and shading devices. And based on that, we come together and publish this guideline in order to reduce this performance gap and take the initial step to reach this goal. For all of the thermal modeling studies, having the performance specification of the blind is important as much as knowing the software assumption and simplification. And we hope that this guideline will give you some information and useful information in order to guide you to have a better model and reduce the performance gap. In this study, we have mentioned the basic blind, which is defined as any type of blind, but of only one layer and limited to moving up and down, which can be similar to roller blind or closed Venetian blind. The second section of this publication covered the heat transfer through glass blind system, and which means that all of the heat transfer mechanism and a background knowledge on the building physics for the heat transfer through the window and blinds, which include both heat gain and heat loss through the blinds. The third section of this publication is covering the modeling inputs. All of the modeling inputs that you may need for modeling shading devices and blinds. The first part is solar properties of glass blind system, including glazing G-value, G-tot, and shading coefficient. The second part is the thermal performance properties, including blind thermal resistance, thermal emissivity, air permeability of shading, and perimeter gap. The last part of this section also provides you with the useful online resources to find the blind performance data. Section 4 gives you some information on the representing a blind in a dynamic thermal model. including software limitations, workflow, and important parameters, and representing real operation and installation of the blind. There is also a how-to section which answers the possible question that a modeler may come up, such as how to choose the most appropriate tool for the study, or how to represent the glass blind system you value. I'm not going through all of these points, but we hope that this guideline will help you to sort out the answer and find the guideline, the positive guideline for your modeling. Section 5 covers the best practice usage with other applications. For example, for your model or your study, you may come up for the natural ventilation. You need to know that blind can have a major impact on the achieved effective area, especially when you have an open window and closed blind. And this will cover the thermal comfort, visual comfort, or energy as well. Last section of this publication is the emerging themes with all of the additional consideration. For example, to reduce the energy performance gap, it's important to know and consider the uncertainty of blind operation. For example, you may model a blind that particular blind is automated, but in reality, you will have some manual override as well. So this will increase the uncertainty of your model. So you may need to consider all of these issues and be aware of it. And also time-varying nature of blind dynamics within the building simulation. I'm not going through all of the points, but I just want to let you know and inform you that with having this publication, we noticed that there is plenty of opportunity to improve blind application through further research and development. And we hope that in next steps, we will reduce the performance gap with having more researchers and studies in this aspect. The most interesting part is the launch activities. We are going to have a webinar, Grow Your Knowledge webinar through CIBSE, and next year, 21st of February, from 11 to 12 p.m., 11 a.m. to 12 p.m. You may need to add it to your calendar, don't miss it. You will receive a notification from CIBSE as well. There is an interview with the authors as well, that if you are interested to know what's the behind the scene of being a CIBSE technical memorandum authors, you can read it, and I think it will be available from tomorrow in the next knowledge newsletter. We're probably gonna have another launch event that will be confirmed in the near future. Thank you so much for listening. Yes, the emails are quite full, but you can contact us for any further question. Thank you so much.
You can blame me for the white font. I don't know why this is happening, so you have just to give me a quick second to load up the awards page.
Thank you everyone again. So I will be announcing the commendations and the Young Modeler Award. To me, this category is explicitly important because it's recognizing the future superstars of the building performance simulation. So for both shortlisted candidates, they all submitted excellent entries, and it was a pleasure to review all of that. And we are impressed by the inputs and the recommendations of the candidates. So for the commendations, we have Anmol Mathur and Priyanka Devi Murugappan. And now it's time to announce the winner of the year's Young Modeler Award, and it's Shivita Salvankar. Thank you for your detailed response and capturing modeling skills and sharing your future plans on the promoting sustainability. Thank you. again.
I don't know what to say actually.
Your family, your brother, your mother.
That reminds me, can someone please take a picture of me because I have to send it to my family. Yeah. Firstly, when I started working on this project, it was mainly because I realized that there was a big gap between what I'm learning here versus what is actually happening in India right now in terms of carbon. Like, we have miles to go, especially in terms of our guidelines. So that was the basis of why I started working on this project in the first place, because I thought, as I am from there, as I was practicing there, now that I'm here and I have this knowledge, why not make something that will actually help someone? Why not do research on something that will help someone develop something which has low carbon, which can actually be sustainable and not just say that it's sustainable. That's the main thing. And so I started working on that, and I'm really thankful to my professor, Dr. Esher Latif, for guiding me through this. And it is sort of sounding like a Oscar speech. I'm so sorry.
Please don't cry. Please don't cry.
I'm so emotional right now. I'm a bit under the weather. I'm sorry. Thank you so much.
This is exactly what I want to hear from, I think, young generation in terms of trying to promote truly sustainable solutions. There you go.
Well, I have to say, for someone that didn't know what to say, had some fabulous words there about how I think we can all step up to address the challenges that we've got ahead of us. So I'm presenting our two runners-up for the Building Simulation Award. And I would just like to say that everyone who has presented here tonight for the Building Simulation Award, just remember, you're all finalists. So feel free to go around and say that you as a finalist and you presented at this event and be proud of it. Doesn't matter what you say, it's the fact that you're here and it's the fact that you've been recognised and asked to come and do this presentation. So our first runner-up.
Is it in particular order? It's not in order, right?
No, the two runners-up are not in order. To be clear, Jonathan Reynolds. Congratulations, Jonathan. So I have to say that I think we all struggled with everyone. It was. I mean, pressure for those 10 minutes where we had to choose the runners-up and the winner. Very difficult. And I think Jonathan and James, your presentations actually were very similar, and on the work that you've done is very similar. And I thought that it was, both of them were fantastic, but Jonathan, you did just pip it to the post there in terms of getting the runner-up spot, so congratulations. Next runner-up, Vishali Mahendra. Congratulations. So HVAC modelling in the UK is something we haven't done enough of. And we shy away from too much. But when you join that HVAC modelling with actually trying to estimate what the building is actually going to do and how it's going to perform, just adds an extra layer on top. I'm pretty convinced myself that this is the way that we're going to have to move in terms of designing buildings. And I just think that the amount of detail and effort that went into getting it right just deserves recognition, so well done. I'll now hand over to Vishali for the final.
I'm worried I'm going to press the wrong button. Yeah, thank you, Darren. Yeah, it wasn't an easy choice, but we really enjoyed, and we're really pleased that the efforts were concentrated in applications that look into pressing issues of today, like thermal comfort, energy demand reduction, and all very relevant in the climate crisis context. So thank you all for that. I don't want to keep you.
You want drum rolls?
Yes, where's the drum roll? So congratulations to Daniel Sanchez Garcia for the presentation of Active. You won, Daniel. Yes, we thought the application to be...
I think you're mute.
I'm mute.
Sorry.
Can't hear anything yet.
Well, you won. Yeah, we'll let you say a few words if we manage that. Yeah, so I was saying that we really enjoyed the innovation and the application of thermal comfort analysis in your work that also results in significant energy demand reduction, and we think that this is something that can have further application and is something that we're going to be looking to be doing in the future. So well done, you won again.
I didn't hear anything before, so I'm not sure. I mean, did I win?
You won. Yeah.
Oh, okay. That's amazing. Thank you. Yeah, I didn't know. Well, I don't know. I don't know what should I say. To be honest, well, should I thank? If I have to thank, I will thank all the people that helped me with this Python library, and well, I think the person that has helped me the most has been my wife. So thank you for that. Well, I think this is a good opportunity. I mean, this Python library is a good opportunity to contribute to the mitigation of climate change, because as we know, in the next years, we're going to have a huge increase in the cooling energy demand. So this is a tool that might help to contribute to reduce this increase in the cooling demand. And well, I hope you enjoyed the presentation, and if anyone has any doubt about the tool, you can contact me, as I said in the presentation, by mail, and we can stay in contact. Okay?
Thank you very much.
Thank you.
Thank you all. Dan, would you like to close the event?
Before you do that, can I ask at least the winners to stay here so we can take a photograph all together? Thank you. We'll hold the laptop like that, so just almost like you're the screen. Don't worry.
Wow. What a fantastic award ceremony there, and a massive congratulations to all the candidates that have put forward not only themselves but their projects, their project teams as well. So well done to everyone there. I've got lots of people to thank. First of all, the executive team at Building Simulation Group. In particular, I'd like to point out Alex, who again has done an amazing job. Everyone's worked hard. Yeah, we have 6 months in the planning, and the last few weeks there's a lot of emails. I'd like to thank our judges, in particular Vasiliki here, who's our head judge, and obviously all the reviewers that went into all their reviewing. I'd like to thank CIBSE, and in particular Javier, who's our group representative, because they've been fantastic. And before I finalise my thank yous, just a quick call out to you. Bahare was talking about in TM69 a possible event next year, so I've got a double call. One, if you can feed back to any of the co-authors what you think about the publication. So we may be wanting to do something around maybe March next year. And also if you've got any non-basic blind applications, we can, anything good on the basic blind applications that you think is covered, but also the non-basic blind applications, because we always like to look forward to what we could be doing in further publications. And finally, a massive thank you to our sponsors, Design Builder, EDSL, ECI, IES, and Monodraft. All the winners get a little monetary prize, but we'll also be asking our young modeller, well done, to join us in our committee meetings over the course of the next year, and hopefully she'll get an insight into what we talk about behind closed doors. So it's just to bring it to a close, Building Simulation Awards 2022, and hopefully see and speak to you later. Thank you.